In this video, we're going to be going over problem 2B.3, laminar flow in a narrow slit. If you're in transport 1, this is like if your teacher doesn't assign you this problem, that'd be pretty surprising. It's like pretty common problem that they assign. All right, so laminar flow in a narrow slit. Part A, Newtonian fluid is in laminar flow in a narrow slit formed by two parallel walls, distance 2b apart. Understood that W is much larger than B, so the edge effects are unimportant, and make a differential momentum balance and obtain the following expressions for the momentum flux and velocity distributions. So what it means by edge effects being unimportant is that the velocity is only going to depend on the x direction, so it's only going to depend on these larger walls, and it's not going to depend on these walls here, like this short wall. So what that means is that the velocity is only going to depend in the x direction, and it's not going to depend in the y direction. So yeah, that's basically what that means. So we need to find tau xz and vz as well. So tau xz is the vz with respect to x. So let's go to the actual problem. So yeah, assumptions, assuming laminar flow, vz is a function of x in this direction, x. Yeah, so we have this differential volume, and that's like the volume that the momentums and the gravities are going to be acting upon. So as you change x, as x increases, this differential volume will go across, and it'll cover the whole solid. So dx is basically just an infinitely small value. Obviously this isn't infinitely small, I'm just making it so you can actually see it. So as you increase x, this differential volume moves across the surface and through the solid. All right, so since we have vz is depending on x, and the pressure is depending on z, because the pressure is depending on z because it's just like a regular ocean, or just like water. As you get deeper in the water, the pressure is greater. So we have to find the area perpendicular to the x direction and the area perpendicular to the z direction because of that. So the area perpendicular to the x direction would be like this face here. It's kind of highlighted, but not really. That's just L times W. AX equals L times W. And just like a sanity check, for at least for these 3D rectangular shapes, if it's AX and X is like the differential X, it's never going to have its own dimension inside of it. The X is not going to have the X dimension, and the Z is not going to have the Z dimension. So AZ is W delta X. So in the Z direction, that's down. So this is like this face here, but it's like partial. It's only part of the face. It's delta X times W in the Z direction. Looking down, this is like from above, this is the face that you see, delta X W. Yeah, and then the volume, we need the volume as well because there's a gravity force. So, and the gravity is applied over the whole volume. So momentum fluxes and shear stresses and all that kind of stuff, it's applied on a face, but gravity is applied on a volume. So now we're just doing our shell balance. So it's momentum in minus momentum out plus gravity equals 0. But in this case, it's negative gravity because um, the coordinates are from top down. So like if z increased, um, if z increased like with height, with like just regular height, it would be plus rho gz. And by the way, this z is supposed to be like a subscript. I just didn't for whatever reason. It should be a subscript though. So yeah, that's why this is negative. And then just the standard momentum flux thing. So yeah, that's just like in minus out, and then in minus out um, at z equals 0, z equals L, and then x equals x, and x equals x plus delta x. So that's where those come from. So it's in minus out, momentum in minus momentum out, plus the gravity. But in this case, it's minus because, again, the gravity coordinate, or the coordinate for the z, starts at the top and goes down. If it started at the bottom and went up, then it would be plus, which is, it's normally going to be plus in most problems, but in this problem, that's an exception. All right, so we need to define the momentum fluxes now, just to simplify the equation. So I usually look at 17.3 or 1. Usually look at 1.7-3 A and B for this. So yeah, okay, 1.7-3 A and B. So our momentum fluxes are, what are they? Our momentum fluxes are ZZ and XZ. So the reason this is ZZ is because the pressure is changing in the Z direction due to the Z direction. So it's changing in the Z direction due to the Z direction. And the other one is XZ, the ZZ term, because both of these are the same. There's going to be a P, there's going to be a pressure, and obviously pressure exists. So that's why this momentum exists. All right, so yeah, back to the 1.3, 1.7-3. So momentum flux XX. So you can just interchange any of these. Like you could say ZZ, you could say XZ, you could say YX. Like just switch out the letters for whatever you want. It's just the only difference is the same letters and different letters. So for momentum flux in the ZZ direction, don't bother really looking at this first part. Look at the second part. It's pressure plus tau ZZ plus rho VZ VZ. And for the XZ direction, it's tau XZ plus rho V X VZ. This should be VZ in our case. Yeah. So momentum in the ZZ direction is pressure plus tau ZZ plus rho VZ VZ. And tau ZZ is 0 because this term goes to 0 because the V in the Z direction, the VZ does not depend on Z because it only depends on the walls. Because of the law of the wall, the water gets slowed down by the walls, not by distance up or down. And yeah, you can look at table B1 for this equation. I guess I can look at that as well. Yeah, okay, so tau ZZ is table B1, dVZ dZ, and this whole term goes to 0 when you have a Newtonian fluid. When the fluid is assumed to have constant density, this term goes to 0. So we're assuming it has constant density and it's Newtonian, and that assumption, it says Newtonian fluid, so that's why we can assume that term is going to 0. So obviously I just didn't even write it there. Based on analysis system, VZ does not depend on Z, and that term goes to 0. So pressure will change with Z because it's an enclosed container, like the walls are enclosed. Rho VZ, VZ will cancel because, again, VZ is not dependent on Z. So if you look at these terms, this will have an identical rho VZ, VZ to this. So they'll just subtract out and they'll equal 0. And that's why you can kind of just cancel out this term, even though technically they subtract. Like there's the term is, it's like rho VZ, VZ minus rho VZ, VZ. But yeah. So now going to the momentum flux XZ, you have tau XZ plus rho VX, VZ. And this doesn't have a P because these two symbols here are not the same. And it's like the sigma thing, where if they're not the same, the sigma equals 0, so the pressure equals 0. And if they are the same, the sigma equals 1, so the pressure exists. And this term goes to 0 because there's no V in the X direction. And so momentum flux in the XZ direction equals tau XZ. And tau XZ from table B1 equals negative viscosity dvx dz plus dvz dx, and this term goes to 0 because there's no vx. Yep. There's no velocity in x direction. All right, so now we're plugging in the expanded definition. So we're just plugging in this. This goes into here, and just this goes, and all that goes into here and here, and we're not doing anything with this yet. Yeah, that goes into there, that goes into there, and then yeah, that's canceling because they're the same exact term. And then we divide by the volume, which is LW delta X, and then we can convert to the derivative form. So we're dividing by the volume, and you'll see X, and then there's the X coordinate, and then there's these X's here, and then there's the delta X in the denominator. So that's how you know you did it right. The delta X has the X coordinates up top. And I just condensed the notation here. So P adds equals 0 minus P adds equals L. That's just kind of like a common thing you'll see in the textbook. And then, yeah, just minus rho GZ. All right, so yeah, and then you convert it to a derivative. So when you do a derivative, basically the sign flips. So in the momentum balance itself, it's in minus out equals 0, or in minus out plus gravity equals 0. But for a derivative, it's out minus in divided by the derivative, or divided by the differential length. So wait, not the differential length. It's final value minus initial value over final length minus initial length. So this is the differential x is the x plus delta x minus delta x. Or no, x plus delta x minus x. And the x plus delta x is the final value, and the x is the initial value. Like that differential area where the bounds of the volume is x right here, and then it's x plus delta x. So final value x plus delta x minus x equals delta x. So that's where that. Well, you're like working to get that form from here. Like you're not just like, you're working to get that form here. Like you don't just, I don't even know what I'm trying to say here. Like this form just represents delta x. It's not x plus delta x minus x. It's just you're working to get this form to just be this. All right, so basically, I just rambled a shit ton. But yeah, this is. Does that make sense? Yeah, that makes sense. So yeah, normally this would result in a positive derivative because you're moving this final value. Um, it's the final value minus this. Does that make sense? Final value minus that. Yeah, and then you add an. Yeah, that makes sense. And then the negative sign is just because I moved it over to the other side. Yeah, okay, that makes sense. So now you're converting this to modified pressure. Um, there's like a couple places in the book where it says that. I'm not sure exactly where. Let's see. Fine. Okay, so yeah, delta modified pressure equals pressure plus rho gz, and it's minus in this case because the coordinate system is from the top, and you can just do some algebra for that, but it works out if you say delta pressure equals that. So like z is uh, yeah, it's minus in this case because the coordinate is from the top. So just I don't know, just trust me on that, man. Um, yeah, so just transform this to that. All right. All right. So now looking at this equation, there's going to be two boundary conditions because we have a derivative here and we have a derivative here. So you have to integrate twice, or separate and integrate twice. So first boundary condition is going to be at the walls. So at each of these walls, plus or minus b, because this is plus b right here, wall. This wall is plus b. This wall is minus b. Um, the law of the wall is that the liquid at the wall is going to move at the same speed as the wall, and the wall is not moving. So the velocity at the wall is going to be 0. And then the second boundary condition is at x equals 0, tau xz equals 0. Um, so yeah, at x equals 0 in the center of this, tau x equals 0. And that's because tau xz is the viscosity times the derivative of x, the derivative of vz with respect to x. So picture the velocity, the velocity doing like the velocity profile doing like a kind of curve like this. So it's going to be the highest in the middle, farthest away from each wall. So the derivative of that equation is going to be a horizontal line at the maximum, which is x equals 0. And obviously, evaluating a horizontal line is going to be, the value is going to be 0. The slope, the derivative, basically the derivative at a max is 0. So the velocity is at its max at x equals 0 because x equals 0 is farthest away from both walls. And at a max, the derivative is always going to be 0. And at a local min, the derivative is always going to be 0. So yeah, that's why the velocity, or why tau xz, which is the derivative of vz with respect to x, is 0. Where's the tau xz? Yeah, so derivative of vz with respect to x, and that's going to be 0. Because at a maximum velocity, the velocity's derivative is 0. So now we just integrate, separate and integrate. So you just multiply the dx over to this side, and you take the derivative of this, which is just going to be this by itself. The integral of dx is just x. So integral of all this is just going to be all this. And then the integral of this is just, obviously, you just multiply by x. And then you have to add the C1. And if you do an integral on both sides, you only have to have one constant, because obviously you're going to have a constant on this side, you're going to have a constant on this side. You just add the one over this side to this side. It's the same thing. It's just having one constant. So now we're employing the second boundary condition here, which is this boundary condition. And you're not always going to be able to use you're not always going to be able to use a boundary condition at the first integration, but because tau x z equals negative mu dvz dx, it equals the derivative that's already in this equation, we can employ the boundary condition. But if you have two boundary conditions that are like this, where it's just vz equals 0 at a x, you're probably not going to be able to use a boundary condition like mid-integration. So yeah, tau x z, why is my mouse not working? Tau x z, which is this, equals 0 when x equals 0. So you're just plugging in 0 for that, 0 for this, and we get C1 equals 0. So we can plug in C1 into this equation, and it's just 0. So that just makes integration easier. And that's the answer for part A, or one of the answers for part A. That's this answer here. Obviously, it's the same answer. Yeah, so now we're going to separate and integrate again. You need to isolate the derivative first and then multiply the dx over. And yeah, so it's just another x squared divided by 2, and then plus another integration constant. So now we're employing the second boundary condition, which is, or the first boundary condition, at x equals plus or minus b, vz equals 0. And then, again, that's the law of the wall thing, where the liquid moves at the same speed of the wall, unless it's like turbulent, which is not. It's not turbulent. It's said in the problem description. So plugging in 0 for vz and b for x squared. Obviously, it's x squared, so it'll be b squared, whether you put negative b or positive b. So that kind of works out. Isolate CT, you get this, and then you just insert this back up here. You get this, and then you want to factor out like a common thing. So I just factored out this pressure conglomerate thing. And then from here, I'm just trying to get it into this form. So I see I just divide by b squared basically, or I divide b squared out of the parenthesis and multiply it up here. You can do that. I divide b squared out of the parenthesis, so it's 1, and you're having to divide b squared here too, and then you multiply it outside. And x squared divided by b squared is the same as this. So yeah, form matches. All right, so that's the answer for part A. So average velocity, part B. What is the ratio of average velocity to maximum velocity? So basically the way you find average velocity is you integrate over the differential area, and that gives you volumetric flow. And then from that, you can find average velocity. Yeah, so we're just integrating velocity over a differential area, and that differential area is the area that's perpendicular to the flow direction. So that would be like these areas and this area. It'd more be like a slit instead of like what I highlighted over here. Yeah, it'd be like a slit, delta x b, and it would like translate over this whole surface here, so it would cover the whole surface. So from this we can see that This here is delta x, and this is w, so dA equals delta x w, or delta x times w, obviously the area here, delta x times w. And delta x is the same as dx. So q equals the integral of vz w delta x, and the bounds of delta x are from b to negative b. If you look at the coordinate system, this is b, this is negative b. So in the x direction, the bounds are b to negative b. So yeah, now we're just integrating basically similar thing to what we did when we were doing the boundary conditions and all that. W dx. Yep. Take out all the terms of the integral that will not be affected by the integration. So things that you could divide or multiply out, things that you can add or subtract out, you can't really take that out of the integral. So I can take out this out of the integral, but I can't take this out of the integral. Or you might be able to multiply by b squared, but I didn't do that. I just didn't do that, basically. You might be able to do it, but I don't think it's convenient if you can. So yeah, we're just integrating this now. I designate this as alpha just so I don't have to write it over and over again. Integrating. Yeah. I don't know. Look at that. It's just math. So yeah. So then Q, the volumetric flow rate, which is in meters cubed per second, equals this. So now average velocity can be found by dividing volumetric flow by the area perpendicular to its flow direction, which is AC, which is these areas, which is the x direction and this direction. So if you go over here, it is 2b times w. And yeah, here we see 2b times w is AC. So yeah, that checks out. That's what I put earlier. So yeah, Vz equals 2bw, 1 divided by 2bw times q. And we're just doing some algebra there. And so the average velocity equals that. And yeah, so remember that Vz max is just the velocity at x equals 0, and that's because that's the coordinate where the liquid is farthest away from either of the walls that are going to be affecting the velocity or slowing down the velocity. So basically, we just have to plug in x equals 0 to the regular velocity equation, which just plug in x equals 0 to here. So it should just be just this alone, because x equals 0, this 1. It should just be this alone, this term alone. And it's asking, what question B is asking us for the ratio of average velocity to the maximum velocity. So G equals this. Yeah, so you just multiply the wait, does that make sense? Average velocity. Okay, yeah. You just multiply this times the inverse of this because it's the denominator. And average velocity equals 2/3 Vz max, and you're just canceling terms there. Yeah, just cancel terms. It makes sense. So yeah, that's answer for part B. Now part C, obtain the slit analog for the Hagen-Poiseuille equation. So the Hagen-Poiseuille equation is just a mass flow equation for the flow in a pipe. So we're looking for the mass flow equation through this slit, I guess. So that's what we're doing. That's why this is W. This W is a mass flow. That's what that means. It means mass flow. And mass flow is just the volumetric flow rate times the density. Volumetric flow rate times the density. And you could just see volumetric and then mass flow. You multiply them together, meters cubed. The units cancel on kilograms per second, and kilograms per second is mass flow. So yeah, you just multiply Q times W, and you get mass flow. It's pretty simple. Yeah, Q up here, and then you just multiply by rho. It's pretty simple. Yeah, so that's the answer for that. All right, so now part D. Draw a meaningful sketch to show why the above analysis is inapplicable if B equals W. So if B equals W, it'll look something like this, where this is B and this is W. And obviously, if these walls are this big, the friction from these walls is obviously going to affect the velocity profile of the liquid going through here. So the liquid is going to be slowed down by this wall and this wall. So VZ is going to be dependent on the Y direction and the X direction. And obviously, we just had it as dependent on the X direction. So the whole equation is just not going to be valid. I think I just pretty much repeat what I just said there. All right, in part E, how do the results in B, how can the results from B be obtained from the results in problem 2.5, example 2.5? So basically, we can just use the same equations. We can just use these equations. And so this problem 2.5 is basically just saying that there's two different viscosities, or two different regions, two different liquid regions that are separated because there's different viscosities in the regions. So in our case, if we just say these viscosities are the same, these are the same, these are the same values, it'll simplify to our equation. So I think I wrote that out here. Yeah, so modified 2.5-2, VZ, it should be this, 2.5-20. Yeah, it's just 2.5-20. So you're just saying all of these are the same again, like I just said earlier. So this would be 2 viscosity plus 8 viscosity. And we see that here, 8 viscosity over 2 viscosity. And VZ equals this. And then this is the same average velocity we calculated for part B. So yeah, that makes sense. Divide by VZ max to get the ratio. And yeah, that's the problem. I don't think I did actually VZ. Well, actually, you can just go VZ. Yeah, so this term will cancel, and it'll just be 1 because it'll be 2 viscosity plus over 2 viscosity. So this will go to 1. This term will cancel out because it'll be 1 minus, or viscosity minus viscosity. So this term will cancel out, and then it'll be the same equation as before, basically. Yeah, so it'll be the same equation as before for VZ, and then you plug in 0 for X, you get just this term alone, and then it's 1/2 divided by, or VZ, or no, it's 1/3 divided by 1/2, and that's 2/3. So yeah, that's the same value. And yeah, if you have any other questions about this problem or any other problems, feel free to leave some comments. If you want any other problem solved, feel free to request it. First 3 chapters of each section are my specialty, in terms of what problems I can solve, but I can solve other problems too. I've done so for some other classes less rigorously than Transport 1. Um, yeah, have a nice day. Bye bye.